Welcome to this next lecture on acoustics. We were looking at the derivation of the Kirchhoff-Helmholtz integral equation, and so last time we ended up with two surface integrals. Okay, this is number 1 and this is number 2. This surface integral is over the outer surface here, this outer surface, whereas this is over the around the singularity with the radius of epsilon and this limit epsilon going to 0. And we were looking at this term. So this is the total term 2 here, this is the total term 2 here. So this is term A within that and this is term B within that. So if I rewrite this, we have integral S epsilon limit epsilon tending to 0 phi gradient of 1 over 4 pi e to the power of minus j k epsilon by epsilon dotted with n minus 1 by 4 pi epsilon e to the power of minus j k epsilon gradient of phi dotted with n over epsilon sphere, surface of the sphere, and this is epsilon square sine theta d theta d phi. Okay. So now what happens, let us, so we said this is term A and this is term B. Okay. And so now what happens is, if we consider the term B over here, which is limit epsilon tending to 0 integral over that surface minus 1 by 4 pi epsilon e to the power of minus j k epsilon gradient of phi dotted with n into epsilon square sine theta d theta d phi so that becomes equal to, we are integrating around a singularity at r dash. Okay. And phi and del phi are well behaved by the theorem or Green's identity, well behaved, and therefore as epsilon goes to 0, this del phi dot n comes out and del phi dot n acquires the value at r equal to r dash. Okay. And I have limit epsilon tending to 0 integral S epsilon minus 1 by 4 pi epsilon e to the power of minus j k epsilon into epsilon square sine theta d theta d phi. Now epsilon falls out. There is a cancellation over here, one epsilon remains on top, and so what we have is this well behaved function evaluated at r equal to r dash, limit epsilon tending to 0, epsilon comes out, integral s epsilon minus 1 by 4 pi e to the power of minus j k epsilon sine theta d theta d phi. Now this is a well behaved integrand and it will integrate to a finite value, whereas there is an epsilon in front that is going to 0, and this is a well behaved value, and so this integral goes to 0. This integral here goes to 0. Okay. So now we are left with this next term. The second term, which is term A, okay, is limit epsilon tending to 0, integral s epsilon phi gradient of 1 by 4 pi epsilon e to the power of minus j k epsilon dotted with n, and again epsilon square sine theta d theta d phi. Now we did say last time that del by del n is equal to minus del by del epsilon. Okay. So what happens first here is this entity is minus del by del epsilon of 1 by 4 pi epsilon e to the power of minus j k epsilon. So if I keep the minus 1 by 4 pi outside, what I get is minus e to the power of minus j k epsilon by epsilon square minus j k e to the power of minus j k epsilon over epsilon. So this cancels off, so we get a plus here, and that is this portion. So what I now have is limit epsilon tending to 0 phi, which is actually a function of r, then this thing that we found 1 by 4 pi e to the power of minus j k epsilon by epsilon square plus j k e to the power of minus j k epsilon by epsilon into epsilon square sine theta d theta d phi. Okay. So now again phi of r is a well behaved function, well behaved, by Green's identity, and so as epsilon goes to 0, it acquires the value at phi r dash. okay, and there is an integral sign which I missed, S epsilon. Okay, so this acquires the value at r dash, so we keep it outside. It is well behaved. It in the limit it acquires this value, we keep it outside the integral. Then we have limit as epsilon tends to 0, integral S epsilon, and I'll keep 4 pi also outside, e to the power of minus j k epsilon by epsilon square plus j k e to the power of minus j k epsilon by epsilon square sine theta d theta d phi. Now if I bring epsilon square inside, then I have a cancellation here and I have an epsilon here, okay, and with epsilon tending to 0, what we will get is this term cancels out. So I have phi of r dash by 4 pi limit epsilon tending to 0, integral S epsilon e to the power of minus j k epsilon plus epsilon j k e to the power of minus j k epsilon sine theta d theta d phi. Okay, this can actually be done as epsilon is an integral over the surface. So this is going to be 0 to twice pi for the phi integral and 0 to pi for the theta integral. So it can be done, and the front part, this part is independent of theta phi, so it can be taken out. Okay, so let's see how this looks. Okay, so as I was saying, this is the integral we have with d theta d phi, and d theta goes from 0 to pi, whereas d phi goes from 0 to twice pi, and this term are independent of theta phi, so they also come out. So to do it formally, I have phi r dash by 4 pi limit epsilon tending to 0 e to the power of minus j k epsilon plus epsilon j k e to the power of minus j k epsilon and integral 0 to, let's say, pi, and integral 0 to twice pi sine theta d theta d phi, and this gives me 4 pi, which cancels with this 4 pi, and I have this limit over here which ends up as now phi of r dash into 1. Okay, this goes to 1 and this goes to 0. Okay, so now in the finality, what do I have? I have integral, okay, phi del psi dot n minus psi del phi dot n over the outer surface ds plus phi r dash plus phi, this is phi at r dash is equal to 0, or phi r dash is equal to integral over the outer surface psi del phi dot n minus phi del psi dot n ds. And psi was my green function. Psi was my free space green function, which means phi at r dash is equal to the integral over the outer surface g r comma r dash del phi del phi r dotted with n minus phi del g dot n over ds. Okay. So, to write it in a short way, I will not put all the arguments. G del phi del n minus phi del g del n. I will write it this way, ds. Okay. So this is the Kirchhoff Helmholtz integral equation. So what does it say? What it says is that if I know, let's say, the free space green function, which is g, okay, and is a function of two locations, r and r dash. If I know the free space green function, and if I know values of phi on the surface S, in addition I know del phi by del n on the surface S, then I can find, phi at r dash inside the volume. Okay. So if I have a volume bounded by the surface, this is a volume bounded by the surface S, and on this surface I know values of phi, I know values of del phi del n. Then I can find, so I have the r, which is the rowing integration coordinate r, okay, and I have r dash, which is the location of the singularity. So I can find the value over here, provided I know the values of phi and del phi del n on this surface. Okay. Now, what is the advantage? So this is what it is. We have phi at r dash is equal to integral over s g del phi by del n minus phi del g by del n ds. Now, if phi is pressure, okay, then what I have is the pressure at r dash is the integral of s green function del p del n minus p del g by del n. Okay. And del p del n is what? Del p by del n is minus rho 0 del t of Vn. This is my Euler equation. Okay. And in the harmonic case, it is minus j omega rho 0 Vn. So what I now have is pressure at a location r dash is the integral over the surface g r comma r dash del p del n, which is minus j omega rho 0 Vn minus p, okay, r del n of g ds, which is a function of r. So on this surface now, going back on this surface, if I know the values of pressure and the values of surface velocity, acoustic particle velocity, okay, acoustic velocity, then I can find the value of the pressure inside at a location r dash. Okay. So in order to, so this is the Kirchhoff Helmholtz integral, this is the KH integral, KHI. Okay. So if I know the values of pressure, on the surface and particle velocity, normal particle velocity on this surface, then I can go ahead, I know the form of the green function, I know the form of the derivative of the green function, I perform this integral and find the pressure inside, Okay. So now, whether you can do this in a closed form, okay, if you know these conditions, if you know the pressure, and velocity on the surface S, whether you can do the closed form integral, a closed form integral can be done depends on the situation. However, this can be done numerically, and that is what is the topic of the boundary element method. Because it is a boundary integral, the boundary is discretized, and that this integral forms the basis for boundary element method. Although we are not so interested in the numerics of this, let me just say that at any point, what if I have a box, let us say, and let us say a rigid box, or a room, this is a room, okay, and the walls are rigid and there are windows, let us say these are the windows, okay. Now if the walls are rigid, then I will know del P del N, or the velocity is 0 there, but pressure is unknown. Similarly, where the windows are, the velocity is unknown. However, the pressure is gauge pressure or atmospheric pressure, this is 0. Okay. So at the start of the problem, only one condition is known, only one condition will be known, is known. So in boundary element method, the first half of the problem, or first part of the problem, is to find the unknown information, the unknown part of the information. Where pressure is known, there we try to find the velocity also, and where velocity is known, there we try to find the pressure also. That is first half of the problem. Then on the boundary, everything is known. So we are trying to find the boundary information here, first half, boundary information or boundary conditions we are trying to find. Then in the second half, we use this knowledge of the boundary information of both pressure and velocity, and then we integrate to find the information inside. Okay. So that is Kirchhoff-Helmholtz integral equation for interior problems. Interior problems. In the coming next lecture, we will discuss KHIE for exterior problems. Thank you.